Hello everyone, welcome back to the channel. So in the previous session we have discussed about half-life period of a different reactions like zero order, first order reactions, and even we consider the significance of a half-life period and some important things, that is the relation between half-life period of a reaction, order of a reaction, and concentration of reactant species. So what is that general reaction equation? If you remember, T half is proportional to 1 divided by n minus 1, that is A raised to n minus 1. By knowing this relation, one can specify relation between those three quantities: half-life period, concentration of reactant, and order. Well, so by dealing with factors affecting the rate of a reaction, we consider 6 factors. Temperature is one among them. So there we said the effect of temperature on rate of a reaction. Split quantity we have discussed. So how they are related? Rate of a reaction and temperature, generally both are directly proportional. So in the sense, higher the temperature, more is the rate of a reaction. Less the temperature, less is the rate of a reaction, we said. And further, even we quoted the reason also. What is the reason we said there? Increase in temperature increases the number of effective collisions, I said. Or generally I mentioned collision frequency, number of collisions per unit time. So as a collision frequency increases, hence rate of a reaction increases. So in this session we are going to deal with the effect of temperature on rate of a chemical reaction. That is, effect of temperature on rate of a reaction. Well, when I think of effect of temperature, first thing to be remembered here is, when you look at the thing, as I mentioned, the effect of temperature in the sense is going to influence over the collisions. Increase in temperature increases the collisions. When collision increases, only when kinetic energy of reactant molecules increases, then only number of collisions increases, in turn rate of the reaction increases. But say there are 100 reactant molecules, say consider there are 100 reactant molecules. Whether all reactant molecules are going to have same kinetic energy? No. Some of the reactant molecules, they may have very low kinetic energy. Some are associated with very high kinetic energy, and rest of the reactant molecules may associated with the moderate kinetic energies. Therefore, we say, whenever if I consider reactant molecules, all reactant molecules in a substance do not possess same kinetic energy. This is the first thing to be remembered. So, as I said, we have possibilities. They may have very high, some may have very low, and some may have moderate kinetic energy. That is the average kinetic energy. Further, why it happens? Why you are going to have different kinetic energy? Means during collision, when reactant molecules collide with one another, what happens? Their energy will be transferred from one molecule to another molecules. During collision, what happens? A collision involves transfer of energy. What type of energy? Kinetic energy. Say the one having high kinetic energy, when hits the another molecule of having low kinetic energy, what happens? Part of the kinetic energy will be transferred from first to second. Due to this, during collision, due to transfer of kinetic energy, we are going to end up with the molecules having different kinetic energies. Okay? So what is the said here? It is because during collision, their energies are transferred from one molecule to another molecule. Therefore, there is a distribution of kinetic energy among the molecule takes place. That is, whatever the kinetic energy will be get distributed among all the reactant molecules. Where or when? During collision. So, the kinetic energy will be get distributed among all the reactant molecules. So, it's the second thing. First thing, as we said, all reactant molecules do not possess same kinetic energy. So, what is the reason for this? It is due to during collision, their energies are transferred from one molecule to another. Thus, there is a distribution of kinetic energy among the molecule takes place. Further, if energy of molecules, if you plot a graph of energy of molecules against fraction of molecules with the given energy. Okay. So if you plot a graph of fraction of molecules with the kinetic energy at a particular temperature, we get a curves. Those curves are named as Maxwell's distribution of energies. When we plot a graph of fraction of molecules having energies versus kinetic energy at a particular temperature, we get a curves there. That curves indicates are named as Maxwell's distribution of energies. Okay, well, graphically how it looks? Say, when you plot a graph of fraction of molecules having energies versus kinetic energy at a particular temperature, what happens? We get a curves here. Say, the peak of the curve indicates the maximum molecules having most probable kinetic energy. So fraction, more fraction, that fraction will be more. So indicates the maximum molecules, reactant molecules having a most probable kinetic energy. Okay. Here on either side of the curve, which indicates only small fraction of molecules having kinetic energy or very low kinetic energy. On this side indicates, okay, tail of the curve indicates the fraction of molecules having very high kinetic energy. But the peak indicates the most probable kinetic energy. That is, the fraction of molecules having associated with this peak indicates the fraction of molecules associated with the most probable kinetic energy. So here, what I can say from the graph, what I can say here, having the fraction of molecules having very low or very high energies is very small. Means, look at the either side of the curve. So on this side, what it is? Small fraction of molecules having low kinetic energy. Other side, say, it indicates some other fraction of molecules having very high kinetic energy. So it is the fraction of molecules having very low or very high kinetic energy is very small. The kinetic energy of maximum fraction of molecules at the center of the curve. Okay, whatever the peak area associated with this region, the kinetic energy of maximum fraction of molecules shown by a peak in the graph. What is that peak is considered? It is the most probable kinetic energy. Okay. If I consider this graph specifies at a particular temperature. So at one temperature we get one peak. Further, if we increase the temperature, what happens? There will be shift in the peak. On which side? We know that if you increase the temperature, kinetic energy of the molecules increases. Therefore, what happens? Whatever the peak in the graph is going to shift towards which side? Towards the right side. So, at particular temperature, we get one peak. If you raise the temperature, what changes happens in the graph? There will be more fraction of molecules. Fraction of molecules having energies will be increases, and there will be peak. Peak is going to shift towards the right side. In the sense, the molecules are going to have more kinetic energy. So what I am going to say here, when the temperature is increased, the maximum of the curve moves to the higher energy value. Whatever the maxima is there, is moves to the higher value. Further, the curve moves to the right side. This curve moves to the or shifts to the right side because kinetic energy of the molecules increases. Those two changes happens if you increase the temperature. Okay, which indicates that number of molecules with higher energy content increases. In the sense, if you increase the temperature, the fraction of molecules having high energy also increases. So graphically, how we observe means there will be rise in the maximum and is going to shift towards the right side in the graph. Okay. Well, in this graph, you can visualize that is in a graph of fraction of molecules having energies greater than or equal to activation energy versus kinetic energy. Say at T temperature, say lower temperature, we get a curve here, one curve which corresponds or is going to show this region. This region corresponds to the fraction of molecules reacting or they are involving in a reaction at a T temperature. So is the region. Okay. So it indicates these are the molecules. These many molecules are going to involve in a reaction. So what I can say, if they are involving in a reaction means they have sufficient energy. What is that energy? I can say activation energy. So this region indicates fraction of molecules having energies which is greater than or equal to activation energy. So at T temperature is the region indicates fraction of molecules having energies which is greater than or equal to activation energy, and these many molecules are going to involve in a reaction to give product. Say at T plus 10 Kelvin temperature, it means now what happened? We are increasing the temperature. When we increase the temperature, what happens? That curve going to shift towards the right side. And what about fraction of molecules? Fraction of molecules increases. So graphically how we can visualize? Say at T plus 10 Kelvin. So is the region, the above line, it is the region of molecules occupied. What type of molecules? The reactant molecules having energies which is greater than or equal to activation energy. Now when you compare the first and second region, so obviously it is almost double than the first. So in the at T Kelvin it is the area occupied by reactant molecules, but at T plus 10 Kelvin it is the area occupied by reactant molecules. In the sense, at T plus 10 Kelvin we are going to get some additional molecules. Extra molecules are also involved in a reaction. So what it indicates? For increasing temperature, if you increase the temperature by 10 degree, number of reactant molecules involved in the reaction increases, I can say doubled. So rate of reaction also doubles. Okay. So now we can say from this graph what we can visualize? The increase in temperature of the substance increases the fraction of molecules colliding with energy greater than or equal to activation energy. So if you increase the temperature, what happens? Fraction of molecules involved in a reaction increases, or sometimes doubles or sometimes triples. So overall, what is the conclusion drawn from the graph? Increasing temperature of the substance increases the fraction of molecules colliding with energy greater than or equal to activation energy. Further, what I can say from the graph, it is clear that at T plus 10 Kelvin means at a higher temperature. Generally, at T plus 10 Kelvin, the fraction of molecules possessing energy, okay, greater than or equal to activation energy gets doubled, and hence rate of the reaction is also doubles. So when we increase the temperature, fraction of molecules having energy which is greater than or equal to activation energy doubles, sometimes even triples. Hence rate of a reaction also doubles, and sometimes it is triples, means it increases by 3 folds. Well, so it is regarding effect of temperature on rate of a chemical reaction. Okay. Well, coming to the next concept, that is temperature coefficient. Temperature coefficient. So what it is? Since we can measure rate of a reaction, hence the rate constant at different temperatures. Okay. As we already considered effect of temperature, if you change the temperature, rate of a reaction increases. That is, if you increase the temperature, rate of reaction also increases. Hence, what happens? We are going to get a different value for K, rate constants. So one can calculate rate constant values for a reaction at different temperatures. Generally, how they are related? Higher the temperature, rate of reaction increases. So we are going to get a high K value. Lower the temperature, rate of the reaction is slow, hence we are going to get a low K value, rate constant value. So here we are going to measure rate constant at different temperatures. Generally, say at T Kelvin and at T plus 10 Kelvin. So for the same reaction, so one can able to measure the rate constant at different temperatures. Generally what I said, T Kelvin and T plus 10 Kelvin temperature. If you take the ratio of these, the ratio of rate constant of a reaction measured at two temperatures which differ by 10 degree, or you can say 10 Kelvin. So what I am talking about? I am talking about ratio between rate constant of a reaction measured at two temperatures differ by 10. Is nothing but a temperature coefficient. So what it is? So what the definition says? The ratio of rate constant of a reaction measured at two different temperatures differ by 10 degree is called temperature coefficient. So mathematically, what I can say, temperature coefficient is equal to rate constant at T plus 10 degree Celsius to the rate constant at T degree Celsius. Or I can say rate constant at T plus 10 Kelvin to the rate constant at T Kelvin. So what is the difference between the temperature? 10. Okay. So mathematically I can say temperature coefficient is equal to K rate constant at T plus 10 to the rate constant at T degree Celsius or T Kelvin. So it is called temperature coefficient. So what is to be remembered here is, for most of the reactions, the temperature coefficient, still temperature coefficient values lies between 2 and 3. It means, so what I can say, if temperature coefficient is 2, so for example, by calculating this ratio, if you get temperature coefficient is 2, what it means? For 10 degree rise in temperature, what happens? Rate of a reaction doubles. Okay, for that particular reaction, if you increase the temperature by 10 degree, rate of the reaction doubles. If temperature coefficient is 2.8, what it means? If you increase the temperature by 10 degree, rate of the reaction increases by 2.8 times. So usually the temperature coefficient lies between 2 and 3. So for most of the reaction, the value will be in between 2 and 3. Further, one more thing. So for the calculation of temperature coefficient, we have to select two temperatures. They differ by 10 degree. So what are those most commonly employed temperatures? Means is the 25 degree Celsius and 35 degree Celsius. So what is the second thing remember? Usually the temperature selected to measure the temperature coefficients are 25 degree Celsius and 35 degree Celsius. Well, so what is temperature coefficient? Is the ratio of rate constant of a reaction measured at two temperatures differ by 10 degree. Okay, 10 degree Celsius or 10 Kelvin. It's called temperature. So mathematically how I can represent? Temperature coefficient is equal to K T plus 10 divided by KT. Means rate constant at T plus 10 Kelvin to the rate constant at T Kelvin. And two important things here. One is temperature coefficient of most of the reaction lies between 2 and 3, and usually the selected temperatures are 25 degree Celsius and 35 degree Celsius. Okay. Coming to the Arrhenius equation. So what is Arrhenius equation? So Arrhenius gave quantitative relationship between three quantities. Okay, he specified a relationship between three quantities. One is rate constant of a reaction. Second one, okay, activation energy of the reaction, and third one, temperature. So Arrhenius gave a quantitative, or I can say mathematical relationship between rate constant of a reaction, activation energy of a reaction with the temperature. So what is that mathematical expression? K is equal to A into e raised to minus Ea by RT. So is the mathematical expression. Okay, it specifies the relation between rate constant of a reaction, activation energy of a reaction with the temperature. So is the Arrhenius equation. So what is this? K is equal to A into e raised to minus Ea by RT. So what is K here? So what is K? K is the rate constant of a reaction. What is A is the Arrhenius factor. It is also called pre-exponential factor, or even it is called frequency factor. And what is T? T is the absolute temperature, is measured in Kelvin, and R gas constant. And what is A? A is the activation energy. So what is Arrhenius equation means? The equation which gives a quantitative relationship between rate constant of a reaction, activation energy of a reaction, and a temperature is called Arrhenius equation. So mathematically what it is? K is equal to A into e raised to minus E A by RT. Okay? Well, so here what is to be remembered means we come across that Arrhenius equation. So K is equal to A into e raised to minus E A by RT. So what is that quantity? E raised to minus E A by RT is nothing but it is called Boltzmann's factor. So what it is? Boltzmann factor. What it is? It indicates the fraction of activated collisions. This quantity E raised to minus E A by RT, what it gives? It gives the fraction of activated collisions. Then what do you mean by this activated collision? It is the fraction of molecules having kinetic energy greater than or equal to activation energy. Means the collision which is responsible to give a product. Okay, are called activated collisions. Okay. So Boltzmann factor, what it is? E raised to minus E A by RT. The quantity is called Boltzmann factor. What it gives the fraction of activated collisions, or in turn we can say fraction of molecules having kinetic energy greater than or equal to activation energy. Okay, the one thing. Second one, significance of that A. Whatever we said, Arrhenius factor, pre-exponential factor, or even we said, okay, frequency factor. What is the significance of that A means? It gives the total number of collisions. What it signifies? That Arrhenius factor signifies the total number of collisions, which includes the effective as well as non-effective collisions. Okay, so these are the two important things to be remembered. One is Boltzmann factor, second one is significance of A. Well, so it's regarding the effect of temperature on rate of reaction, temperature coefficient, Arrhenius factor. I hope you understood these concepts. Again, in the next session, we deal with some other concept of a chemical kinetics. Okay, thank you.
Thanks for watching.
Like,
Comments
share,
and
subscribe.